Looks a little bit like a birdie. Here's the picture of the darn thing. So what we're finding the volume of is what's inside this cone and inside the sphere at the same time, the intersection of the cone and the sphere. That's what we're actually finding the volume of. And so first of all, our f of xy is square root of x squared plus y squared. That's how I got this drawing. I had to go into polar graphing to get my actually that's spherical to get my sphere, but there it is. And so the sphere has equation rho equals 3. What I was saying about sometimes this part of the integral is simple, that it was very nice that that happened. Substituting that into the cone equation, the formulas for conversion to spherical coordinates: x equals rho sine phi times cosine theta, y equals rho sine phi times sine theta, z equals rho cosine phi. So that yields the equation rho cosine phi equals, that's z, equals square root of x squared plus y squared. And simplifying this awful mess, notice the rho squareds will cancel out on both sides. We get cosine phi equals sine of phi, because the sine of phi will factor out here and here, and square root of sine of phi will give us just sine of phi. I hope you can see that. And so our phi equals pi over 4. So that means the angle between the pole and where this intersection occurs is pi over 4. So therefore our integral 0 to 3, what nicer limits can you have than that? Rho squared sine of phi, this is just the volume element right here, from here on out. So r goes from 0 to 3, phi goes from 0 to pi over 4, and theta going from 0 to 2 pi. So our first integration, this is going to give us 9 minus 0, so 9 sine of phi d phi d theta. Integral of sine is negative cosine, so it's 9 times negative 9 times cosine of phi, phi evaluated between 0 and pi over 4. And so that would give us, putting in pi over 4, that's square root of 2 over 2 with a negative on it, and minus a negative will give us a plus 9. When we put in 0. So, and that's going to be evaluated for theta going from 0 to 2 pi. So just take this answer we have in here, multiply it by 2 pi, we got 18 pi minus 9 square root of 2 over 2 pi. That is our volume. Now we need the centroid, and if we don't have to make too much of an assumption that the x and the y are both 0, so again, as in the last example, we really just need the z. So the z is rho cosine phi. When we we replace that in our function, of course, notice the limits stay the same, and there's our volume element exactly the same. The only change is we need the rho in here, and this will give us the moment about the xy plane, since z is what we put in there. So multiplying all this out and integrating with, that's p rho cubed, integrating that, we get rho to the 4th over 4, rho going from 0 to 3, so that's 81/4 times cosine phi times sine of phi. And notice from what you might know about little trig identity, that's the same as sine of 2 phi over 2. So now we got 81/8 times sine of 2 phi d phi d theta. Well, integral of sine is negative cosine. I think we already saw that once. And then divided by another 2, so we get negative 81/16 times cosine of 2 phi. Putting in pi over 4, we get cosine of 2 pi, which is 0. So it's 0 minus, when we put in 0, we get cosine of 0, which is 1. So it's 81/16 evaluated between 0 and 2 pi. 81/16 d theta, theta going from 0 to 2 pi, so that would make us 81 pi over 8. So our centroid, x is 0, y is 0, z is this number divided by this number. Now that is one ugly looking z value for a centroid, but it simplifies nicely to, well, I had it simplified a little nicer than that, but I think you can see how I got this answer. Multiply this by negative 1 over negative 1, we'd have positive 9 over 16 minus 8 square roots of 2. So there's our answer.